Hi, this is Professor David Farina. In today's video, we're going to be discussing Jovian moons, rings, and Plutoids. Let's get started. There are four main Galilean moons of Jupiter, and as their name implies, these are the four moons that Galileo saw through his telescope in the early 1600s, and they were one of the pieces of evidence that helped to make the geocentric model of the solar system obsolete. They are Io, Europa, Ganymede, and Callisto, and Jupiter actually has over 24 moons that we now know of. These are the four largest of them, and of interest here is their individual geologies. Each of these different moons has vastly different geologies, and it has everything to do with their distance from Jupiter. So we're going to be discussing that in our video today. And we're going to walk through each of these different moons and check out what is unique about each one. Before I move on, I want you to take note of their sizes relative to the Earth's moon, which is indicated by this little circle here. So you can see here's Earth's moon for scale. So some of these moons are actually bigger than Earth's moon, and of course some of them are smaller. So the first moon that we're going to be discussing today is Callisto, and Callisto is tidally locked to the planet Jupiter, like all of Jupiter's moons, and like Earth's moon is to the Earth. And remember, tidally locked simply means that one side of the moon is always facing the planet, and this is not a very uncommon thing in the solar system. Most moons, in fact, you will find are tidally locked to their parent body, their planet. So what is of interest in Callisto? First off, its composition is very low density, 1.79 grams per cubic centimeter is pretty low, and that has to do with its composition being mostly ice and some rock. It has a very dark surface, and we're going to find that as we look at these outer solar system objects, that the darkness of their surface is an indicator of age. So the darker it is, the older it is. And of course, it's got many impactors as a result of its age. It has been around for a while, and as a result, it's showing the wear and tear of being an older rocky body in the solar system. It has no metallic core, and that tells us that it never really differentiated. Remember, the process of differentiation is changing the density with depth. So if we were to look at the Earth, for instance, there is a higher density core with lower density outer layers. That is not how Callisto is set up. It has not undergone differentiation, and it has no magnetic field. So these worlds, by the way, have been visited by a number of spacecraft, and that's how we have this information. And most of our exploration from now on that we're going to be discussing is all based on spacecraft observation, not necessarily telescopic observation from Earth. When we look at the layers here, it's got a layer of liquid water about 10 kilometers thick, an ocean, if you will, but it's underneath the ice. So it's about 100 kilometers below the surface. And we think that the likely cause of this is due to radioactive decay. So the radioactive decay releases heat, and that heat melts the liquid to maintain its liquid state. The next of our moons is the biggest of the Galilean moons. It's Ganymede, and you'll notice the average density is a little bit higher. It's got a rocky core with an ice-rich mantle over the top of it and a crust of ice. It's about a third of the surface that is an older surface. Once again, the color of it is a little bit darker, which indicates age, and more cratered. But there are parts, about 2/3 of Ganymede are covered in a bright young groove terrain. And if you look back to maybe some satellite images of Earth, you'll notice that these look very much like our glaciers, particularly in particular our mountain glaciers here on Earth. So that's what we're seeing in this picture right about here. And you can see on the surface many, many grooved terrain all over these lighter regions. Now, Jupiter does have tidal effects on its moons, and these tidal effects could be a secondary reason for the moons to have an internal temperature that's higher than what it would otherwise be. And the way this happens is through the process of tidal forcing. The moon is squished and elongated, squished and elongated. And you can think of this almost like kneading bread. And this process of being squished and elongated, as this diagram shows here, it's squished and kind of left back to its normal state. It happens as the moon goes through its orbit. And what that causes is internal heating through frictional forces. It's almost like kneading bread. The second thing that we see as a result of Jupiter's influence is that you're going to have Jupiter, a very large gravitational body, is going to draw in a lot of debris from the solar system in meteoroids. So these meteoroids are going to impact the surface of these moons. And remember, if one side of the moon is always facing Jupiter, that means that the side opposite of Jupiter is going to receive quite a number of impacts, more than the side that faces Jupiter. So when we look at these moons, one side is heavily cratered and the other side is generally less cratered due to this influence of Jupiter pulling in this material through gravity. Next up is Europa, and Europa is my favorite of the Jupiter moons and probably my favorite moon in the entire solar system. And this has to do with the hidden ocean that is underneath of Europa. And it's of a lot of interest to many scientists, and the reason for this is because we think that it's possible life could exist under the icy surface of Europa. And the reason for this is because early Earth would have had a very similar environment where we have some sort of internal heating going on, which is causing hydrothermal vents in our oceans. And it's believed that life probably started at the bottom of the ocean here on Earth near a hydrothermal vent. So it's possible that Europa has undergone that same process, and there are plans to travel to Europa and take samples of its surface. At this point, there's no mission to actually drill through that ice and down into the ocean, but there are some people out there who think this could be a future mission that's much more in the future, and maybe even drop a little submarine into that ocean and swim around for a while. So I would love to live long enough to see a mission to Europa's oceans. Now you'll see the density here has gone up. Its composition is more rock and metal than the other moons. And it is close to Jupiter, and so it's hit by many, many meteorite impacts. So you would expect it to be a very cratered surface, but it's not. And the reason for this is because the surface is constantly regenerating itself. So we've got a very young, icy, very light-colored surface here with very few impacts, meaning this is a dynamic and changing planet, or I should say moon. So here's a little bit more zoomed-in image, and you can see how the grooved and fractured terrain really gives you a good sense as to how much change is undergoing on the surface of Europa here. It has a high albedo, a high reflectivity. So albedo is the word we use for the reflectivity of an object. The higher the albedo, the more reflective it is. The lower the albedo, the more light it absorbs, and the darker it is. Inside of Europa, this is what we think it might look like. The core is not molten. There is no magnetic field, but there is some sort of more metallic core here with a rocky interior, and then a layer of water covered by a 15 or so kilometer surface of ice. So the oceans here are tremendously large. They're much, much more volume than the oceans of Earth, even though this is a much smaller world, because these oceans are over 100 kilometers thick or deep. The next is Io. Now, Io is the volcanic example in Jupiter's Galilean moons. It is constantly active and constantly spewing material. As you can see here, we've got a jet of material releasing itself from the surface, and Io is, as a result, the most active of the Galilean moons. Its average density is once again higher, 3.55 grams per cubic centimeter, so getting up there pretty much triple almost the other moons. And its interior is mostly rock, and it once again has no visible impact craters because it's constantly resurfacing itself. It's light in color with very few impactors. Now, Io has a connection with Jupiter through something called an Io flux tube, where basically what's happening is the magnetic fields of Jupiter are connecting with Io, and the Io plasma torus, or flux tube, is interacting with Jupiter's magnetic field and causing material or ions to flow through this magnetic field. So this is due to the escape of gases from Io and kind of connecting with Jupiter's magnetosphere. So an overall summary here of the Galilean satellites in one image. Take a moment, pause the video, and look over the table 23.2. Okay, now that you've looked at the table, you'll notice that density for Io is the highest, Europa is following a close second, Ganymede is at third place, and Callisto in fourth place for the 4 Galilean moons. And you'll notice that their orbital periods and their distances as a result are starting with Io, Europa, then Ganymede, then Callisto. So it's interesting to see that the higher the density, the closer it is to the planet. Now, these are thought to be second generation. There's probably a first generation of moons that formed around Jupiter. They mostly got lost and sucked in. These are probably a second generation of moon that are actually captured asteroids. So kind of interesting in their formation process compared to our Earth's moon, as we've already discussed. So this is something you'll see in other planets throughout the solar system as well. And here is kind of a picture with some of the other bigger moons in the solar system as well, with Earth's moon in there. You'll notice that can be used as a kind of relationship that maybe you can understand a little better. You can see orbital period here for Earth's moon is significantly greater than anything else in the solar system, even though our radius of our moon isn't necessarily out of line. In fact, it's one of the smaller of the moons in the solar system. Compared to its planet, though, the parent planet radii, it's actually the biggest of the moons compared to its planet in terms of the ratio. So this is kind of an interesting relationship between Earth and its moon. We've got a very big moon. So I hope you have a new appreciation for these Galilean moons. In fact, you can actually see these Galilean moons through a decent-sized amateur telescope. If you know what to look for, it's actually really easy to find. I recommend getting an app on your phone called Sky Safari AR, and it's a free app, and you can just you kind of zoom in on Jupiter, and you can see the Galilean moons. And if you're looking through a telescope, you can kind of match up what you're seeing in the telescope with what's on your phone screen, and it gives you a really good picture of these 4 Galilean moons, and they move within just a few hours, you can watch them move around Jupiter. You can watch them pass in front of Jupiter, which is called a transit, or pass behind, an occultation. And I promise you, this is one of the coolest things that you can see. You can even see the moons casting a shadow onto the surface of Jupiter, which is tremendous. And I've seen this through a telescope a number of times, and I'm always awestruck by it. It's just so cool to see that from so far away. So here are the orbits of those 4 Galilean moons. Here are their interiors. And I'm just going to skip through that one. Here's some other activity on the planet, or I should say moon Io. A zoomed in picture here of a volcano and its plume. Here's another volcanic plume that's zoomed in on. Here's Europa again, with some more pictures of its surface. Here's Ganymede with its grooved terrain. Here's Callisto with its largest crater, Valhalla. And I hope you enjoyed the video today on Jovian moons, rings, and Plutoids, specifically the Galilean moons of Jupiter. Thanks for watching. If you like this video, please click that like button. If you would like to learn more, please click subscribe. And if you'd like to get a notification each time I make a video, please click the bell at the bottom. Thanks again, and have a great rest of your day.